All right, so hopefully you got a chance to try those. So let's go through and do them. And when you first see this, it's a lot to take in. But once you do it a few times, you'll get it. All right, so the derivative. So I can write like this. The derivative of tangent of ln of x equals. All right, equals what? So notice, by the way, I'm not saying tangent of ln of x equals. I'm saying the derivative of tangent of ln of x equals, and then I apply my derivative rule. So remember what I'm going to do. Here's my outside function, here's my inside function, so it's inside parentheses. All right, so do the derivative of the outside function. What's derivative of tangent? I can't remember. Perhaps I will look on my colossal compendium of derivatives, and there's tangent. Oh, it's secant squared. Yeah, I'll have to try and remember that for next time. Okay, derivative of tangent is secant squared. All right, keep the inside function the same. Then multiply by the derivative of the inside function. I often make a note that's g prime, where g is the inside function. All right, what's the derivative of ln x? Oh, I forgot that one too. I better look it up. Ln of x, oh, it's 1 over x. Got to remember that one. Times 1 over x. And you could combine these in various ways, but it doesn't really simplify. You put the 1 over x in front, whatever. But I'll just leave it like that. It's fine. All right, number 2. So it's going to be really common. They're going to ask you, what's the derivative of sine squared of x? We did that before by using a product rule. But, if you have a higher power, you don't want to do that. And also, it's easier if you use chain rule. So now we know how to do it by chain rule. So remembering that derivative of sine cubed x is really the derivative of sine of x cubed. What is the derivative of the sine of x cubed? All right, so what's the outside function here? The outside function is the power. All right, so I'm going to apply power rule by going multiply the 3 out front, keep the inside function the same, and drop this power 1. All right, so that's applying the power rule, the outside function, bringing the exponent out, dropping it 1 using the power rule. But meanwhile, I'm keeping the inside function the same. And then I'm going to multiply it by the derivative of the inside function, which is cosine, so times cosine x. So that's what it is, 3 sine of x squared cosine x. Or most people would at least write that, 3 sine squared x cosine x. Like that. Okay, for your number 3, so here's another one with power rule, right? So you apply the power rule first. So the exponent is the outside function. So I have 5th power. So how do I do that derivative? I multiply out front. I drop the exponent 1, but I keep the inside function the same. So I'm going to have 5 ln of x to the 4th power, keeping that inside function the same, and then times the derivative of the inside function. Derivative of ln x is 1 over x. Oh, hey, look, I didn't have to look it up this time because I remembered it from last time. That's how it works. Okay, and then the last one for secant of x squared I can't remember what it was. For secant of x squared or secant of x squared. It was just secant of x squared. Okay. Number 4, secant of x squared. Okay, so how do I do derivative of secant? Oh, secant is secant tangent. All right, now, so here's one that's a little bit tricky because when I do the derivative of the outside function, it splits into 2 functions, secant tangent. So the x squared stays x squared in both the secant and the tangent. All right, so this is my derivative of the outside function. Derivative of secant is secant tangent. Derivative of secant x is secant x tangent x. Derivative of secant x squared tangent x squared, keeping that inside function the same. Then when I do times the derivative of the inside function, okay, that derivative of the inside function is now written twice, but there's only one inside function. It is x squared, so I'm only going to go times 2x. I'm not going to go like times the 2x like twice or something. Okay, so there you go. That is applying the chain rule. Now, look, actually before we do more things, I wanted to do a couple of fun things. My notes are getting to be a mess now. Let's see, here we go. Getting to be, like they weren't always. Okay, so yeah, here on this compendium of derivatives, we have 2 that we haven't looked at yet. A to the x and log base a of x. Now that we have chain rule, we can show why the derivative of a to the x is a to the x ln a. So it goes like this. What is the derivative of a to the x, where a is any real number? Okay, a is any real number. Okay, well, here's the trick to that. A to the x is equal to e to the ln of a to the x. See, my whole problem is I know what the derivative of e to the x is. E is 2.718, it's a specific number, right? What if the base was a different number? Like what if it was 3 to the x? Okay, anytime you have an exponent with a certain base, you can always write it with base e, because e to the ln of x is equal to x, because e and ln are inverse functions. So that means I can write a to the x as e to the ln of a to the x. Then another cute log property that I can use, I say cute when I mean important, if I have an exponent, I can bring it out to the front of a log, all right? So that's a log property. So look up your log properties if you don't remember that. So that's e to the x ln a, all right? So now what I can do for derivative of a to the x, the derivative of a to the x is really, I'm rewriting it as derivative of e to the x ln a. And now what happens is x ln a is an inside function. So I can get that derivative by taking the derivative of the outside function, losing track of where I put all my different colored pens. They're like all gone. There's not a colored pen on this table. And I was using lots of different colors. I lost a paper today too. Anyway, the outside function stays the same. The outside function we do the derivative of, but the derivative of e to the x is e to the x, so the inside function is just going to stay what it was. It's going to stay the same. But then I have to go times the derivative of the inside function. Well, what's the derivative of x ln a? What's the derivative, huh? What's the derivative of x ln a? What do you think it is? Okay. Remember that ln of a is just a constant, okay? By analogy, what would it be the derivative of x times 4? Well, x times 4 is just 4x. So the derivative of that would just be 4. All right? The derivative of x times a constant is just the constant. This is x times a constant. So the derivative of x ln a is just ln a. Remember, ln a is not a function. It's a constant. All right? Now, what else can we say? This e to the x ln a that we had here, geez, I'm really running out of colors here. I don't know what I did with them all. All right. This e to the x ln a that we have here is the same as a to the x. So I can replace that, a to the x ln a, and that is my formula. So like what do you do with that? What's the derivative of 3 to the x? It's 3 to the x ln 3. What's the derivative of 7 to the x? It's 7 to the x ln 7. All right, make sure you don't get confused between the derivative of x to the third power is 3x squared. The derivative of x to the 7th power is 7x to the 6th, okay? So we use the power rule when x is the base and a real number is the power, okay? We use this rule, the a to the x rule, when the base is a real number and the power is in the exponent. Now, by the way, we all know that derivative of e to the x is e to the x, right? What would happen if I apply this same rule, right? And I said the derivative of e to the x is, so right, 7 to the x, 7 to the x ln 7, 3 to the x, 3 to the x ln 3. E to the x would be e to the x ln of e. What's ln of e? It's 1. Yeah, so this rule sort of explains a little bit more why the derivative of e to the x is itself, because you really always have this like compensating factor of ln of a, but for e to the x is the only number for which ln of that number is 1, and then that compensating factor goes away. All right, more fun with special derivatives coming up.